Chapter 9. Regular Expressions. Some people, when confronted with a problem, think, I know, I'll use regular expressions. Now they have two problems. Jamie Zawinski. When you cut against the grain of the wood, much strength is needed. When you program against the grain of the problem, much code is needed. Master Yuan Ma, The Book of Programming. Programming tools and techniques survive and spread in a chaotic evolutionary way. It's not always the best or most brilliant ones that win, but rather the ones that function well enough within the right niche or that happen to be integrated with another successful piece of technology. In this chapter, I will discuss one such tool, regular expressions. Regular expressions are a way to describe patterns in string data. They form a small separate language that is part of JavaScript and many other languages and systems. Regular expressions are both terribly awkward and extremely useful. Their syntax is cryptic, and the programming interface JavaScript provides for them is clumsy, but they're a powerful tool for inspecting and processing strings. Properly understanding regular expressions will make you a more effective programmer. Creating a regular expression. A regular expression is a type of object. It can be either constructed with the regex constructor or written as a literal value by enclosing a pattern in / characters. Both of those regular expression objects represent the same pattern, an A character followed by a B followed by a C. When using the regex constructor, the pattern is written as a normal string, so the usual rule apply for backslashes. The second notation, where the pattern appears between / characters, treats backslashes somewhat differently. First, since / ends the pattern, we need to put a backslash before any / so we want to be part of that pattern. In addition, backslashes that aren't part of any special character, like \n, will be preserved, rather than ignored as they are in strings, and change the meaning of the pattern. Some characters, such as question marks and plus signs, have a special meaning in regular expressions and must be preceded by a backslash if they are meant to represent the character itself. Testing for matches. Regular expressions objects have a number of methods. The simplest one is test. If you pass it a string, it will return a boolean telling you whether the string contains a match for the pattern in the expression. A regular expression consists only of non-special characters, simply represents that sequence of characters. If ABC occurs anywhere in the string we are testing against, not just at the start, test will return true. Sets of characters. Finding out whether a string contains ABC could just as well be done with a call of index of. Regular expressions are useful because they allow us to describe more complicated patterns. Say we want to match any number. In regular expressions, putting a set of characters between square brackets makes that part of the expression match any of the characters between the brackets. Both of the following expressions match all strings that contain a digit. Within square brackets, a hyphen between two characters can be used to indicate a range of characters, where the ordering is determined by the character's Unicode number. Characters 0 to 9 sit right next to each other on this ordering, codes 48 to 57. So 0 to 9 covers all of them and matches any digit. A number of common character groups have their own built-in shortcuts. Digits are one of them. \D means the same thing as 0 to 9. You could match a date and time format like 01/30/2003 with the following expression. That regular expression looks completely awful, doesn't it? Half of it is backslashes, producing a background noise that makes it hard to spot the actual pattern expressed. We'll see a slightly improved version of this expression later. These backslash codes can also be used inside square brackets. For example, \D means any digit or any period character. The period itself between square brackets loses its special meaning. The same goes for other special characters such as the plus sign. To invert a set of characters, that is to say you want to match any character except the ones in the set, you can write a caret character after the opening bracket. International characters. Because of JavaScript's initial simplistic implementation and the fact that this simplistic approach was later set in stone as standard behavior, JavaScript's regular expressions are rather dumb about characters that do not appear in the English language. For example, as far as JavaScript's regular expressions are concerned, a word character is only one of the 26 characters in the Latin alphabet, uppercase or lowercase, decimal digits, and for some reason the underscore character. Things like E with an accent or B, which most definitely are word characters, will not match \W and will match uppercase \W, the non-word category. By a strange historical incident, \s whitespace does not have this problem and matches all characters that the Unicode standard considers whitespace, including things like the non-breaking space and the Mongolian vowel separator. It's possible to use the \p in a regular expression to match all characters to which the Unicode standard assigns a given property. This allows us to match things like letters in a more cosmopolitan way. However, again, due to compatibility and the original language standards, those are recognized only when you put a U character for Unicode after the regular expression. Using \w for text processing that needs to handle non-English text or even English text with borrowed words like cliché is a liability, since it won't treat characters like E with an accent as letters. Though they tend to be a bit more verbose, \p property groups are most robust. On the other hand, if you're matching numbers in order to do something with them, you just want D for digits, since converting arbitrary numeric characters into JavaScript number is not something that a function like number can do for you. Repeating parts of a pattern. We now know how to match a single digit. What if we want to match a whole number, a sequence of ones or more digits? When you put a plus sign after something in a regular expression, it indicates the element may be repeated more than once. Thus, /\d plus / matches one or more digit characters. The star has a similar meaning, but also allows the pattern to match 0 times. Something with a star after it never prevents a pattern from matching. It'll just match 0 instances of it if it can't find any suitable text to match. A question mark makes part of the pattern optional, meaning it may occur 0 or more or 1 time. In the following example, the U character is allowed to occur, but the pattern also matches when it is missing. To indicate that a pattern should occur a precise number of times, use braces. Putting 4 after an element, for example, requires it to occur exactly 4 times. It's also possible to specify a range this way. 2, 4 means the element must occur at least twice and at most 4 times. Here's another version of the date and time pattern that follows both single and double-digit days, months, and hours. It's also slightly easier to decipher. You can also specify open-ended ranges when using braces by omitting the number after the comma. For example, 5, means 5 or more times. Grouping subexpressions. To use an operator like star or plus on more than one element at a time, you must use parentheses. A part of a regular expression that is enclosed in parentheses counts as a single element as far as the operators following it are concerned. The first and second plus character apply only to the second O in boo and who, respectively. The third plus applies to the whole group, who plus, matching one or more sequences like that. The I at the end of the expression in example makes this regular expression case insensitive, allowing it to match the uppercase B in the input string, even though the pattern itself is all lowercase. Matches and groups. The test method is the absolute simplest way to match a regular expression. It tells you only whether it matched and nothing else. Regular expressions also have an execute method that will return null if no match was found and return an object with information about the match otherwise. An object returned from exec has an index property that tells us where in the string the successful match begins. Other than that, the object looks like and is in fact an array of strings whose element first is a string that was matched. In the previous example, this is the sequence of digits that we were looking for. String values have a match method that behaves similarly. When regular expressions contain subexpression groups with the parentheses, the text that match these groups will also show up in the array. The whole match is always the first element. The next element is the part matched by the first group, the one whose opening parentheses comes first in the expression, and then the second group, and so on. When a group does not end up being matched at all, for example, when followed by a question mark, its position in the output array will hold undefined. When a group is matched multiple times, for example, when followed by a plus, only the last match ends up in the array. If you want to use parentheses purely for grouping without having to show up the array of matches, you can put a question mark : after the opening parentheses. Groups can be useful for extracting part of a string. If we don't want to verify whether a string contains a date, but also extract it, construct an object that represents it, we can wrap parentheses around the digit patterns and directly pick the date out of the result of exec. But first we'll take a brief detour to discuss the built-in way to represent date and time values in JavaScript. The date class. JavaScript has a standard date class for representing dates, or rather points in time. If you simply create a date using a new, you get the current date and time. You can also create an object for a specific time. JavaScript uses a convention where month and numbers start at 0, so December is 11, yet day numbers start at 1. This is confusing and silly. Be careful. The last 4 arguments, hours, minutes, seconds, and milliseconds, are optional and taken to be 0 when not given. Timestamps are stored as the number of milliseconds since the start of 1970 in the UTC time zone. This follows the convention set by Unix time, which was invented around that time. You can use negative numbers for times before 1970. The getTime method on a date object returns this number. It is big, as you can imagine. If you give the date constructor a single argument, that argument is treated as such as a millisecond count. You can get the current millisecond count by creating a new date object and calling getTime on it, or calling the date.now function. Date objects provide methods such as getFullYear, getMonth, getDate, getHours, getMinutes, and getSeconds to extract their components. Besides getFullYear, there's also getYear, which gives you the year minus 1900, such as 98 or 125, and is mostly useless. Putting parentheses around parts of the expression that are interested in, we can now create a date object from a string. The underscore bind is ignored and only used to skip the full match element in the array returned by exec. Boundaries and look ahead. Unfortunately, getDate will also happily extract a date from the string 100-1-3-30,000. A match may happen anywhere in the string, so in this case, it'll just start at the second character and end at the second to last character. If we want to enforce the match must span the whole string, we can add the markers caret and $sign. The caret matches the start of the input string, whereas the $sign matches the end. Thus, /caret \d plus $sign / matches a string consisting entirely of one or more digits. /caret !/ matches any string that starts with an exclamation mark, and /x caret / does not match any string. There cannot be an x before the start of a string. There's also a \b character that matches word boundaries, positions that have word characters on one side and non-word characters on the other. Unfortunately, these use the same simplistic concept of word characters as \w and are therefore not very reliable. Note that these boundary markers don't reveal any actual characters. They just enforce that a given condition holds at the place where it appears in the pattern. Look-ahead tests do something similar. They provide a pattern and will make the match fail if the input doesn't match the pattern. But we don't actually move the match position forward. They are written between $equals and. The E in the first example is necessary to match, but is not part of the match string. The $! Notation expresses a negative look ahead. This matches only if the pattern in the parentheses doesn't match, causing the second example to match only a character that does not have a space after them. Choice patterns. Say we want to know whether a piece of text contains not only a number, but a number followed by one of the words pig, cow, or chicken, or any of their plural forms. We could write 3 regular expressions and test them in turn, but there is a nicer way. The pipe character denotes a choice between the pattern to its left and its pattern to the right. We can use it in expressions like this. Parentheses can be used to limit the part of the pattern to which the pipe operator applies, and you can put multiple such operators next to each other to express a choice between more than 2 alternatives. The mechanics of matching. Conceptually, when you use exec or test, the regular expression engine looks for a match to your string by trying to match the expression first from the start of the string, then the second character, and so on until it finds a match or reaches the end of the string. It'll either return the first match that can be found or fail to find any matches at all. To do the actual matching, the engine treats a regular expression something like a flow diagram. This is the diagram for the livestock expression in the previous example. If we find a match from the left side of the diagram to the right, our expression matches. We keep a current position in the string, and every time we move through the box, we verify the part of the string after our current position matches that box. Backtracking. The regular expression /caret \o1 plus b pipe \da minus f plus h pipe \d plus $, matches either a binary number followed by a B, a hexadecimal number, that is base 16 with the letters A to F standing for the digits 10 to 15, followed by an H, or a regular decimal number with no suffix character. This is the corresponding diagram. When matching this expression, the top binary branch will often be entered even though the input does not actually contain a binary number. When matching the string 103, for example, it becomes clear that only at the 3 that we are in the wrong branch. The string does not match the expression, just not the branch we are currently in. So the matcher backtracks. When entering a branch, it remembers its current position, in this case at the start of the string, just past the first boundary box in the diagram, so they can go back and try another branch if the current one does not work out. For the string 103, after encountering the 3 character, the matcher starts trying to grab the branch for hexadecimal numbers, which fails again because there's no H after the number. So it then tries a decimal number branch. This one fits and a match is reported after all. The matcher stops as soon as it finds a full match. This means that if multiple branches could potentially match a string, only the first one, ordered where the brancher appears in regular expressions, is used. Backtracking also happens for repetition operators like plus and asterisk. If you match /, period, asterisk, x, / against A, B, C, X, E, the period asterisk part will first try to consume the whole string. The engine will then realize that it needs an X to match the pattern. Since there is no X past the end of the string, the star operator tries to match one character less, but the matcher doesn't find an X after ABX either, so it backtracks again, making the star operator just to ABC. Now it finds an X where it needs it and reports a successful match from position 0 to 4. It is possible to write regular expressions that will do a lot of backtracking. This problem occurs when a pattern can match a piece of input in many different ways. For example, if we get confused while writing a binary number regular expression, we might accidentally write something like /01 plus b / period. If that tries to match some long series of zeros and ones with no trailing b character, the matcher first goes through the inner loop until it runs out of digits. Then it notices there is no b, so it backtracks one position, goes through the outer loop once, and gives up again. Trying to backtrack out of the inner loop once more, it will continue to try every possible route through these 2 loops. This means the amount of work doubles with each additional character. For even just a few dozen characters, the resulting match will take practically forever. The replace method. String values have a replace method that can be used to replace part of the string with another string. The first argument can also be a regular expression, in which the first match of the regular expression is replaced. When a G option for global is added after the regular expression, all matches in the string will be replaced, not just the first. The real power of using regular expressions with replace comes from the fact that we can refer to match groups in the replacement string. For example, say we have a big string containing the last names of people, one name per line, in the format last name, comma, first name. If we want to swap these names and remove the comma to get first name, last name format, we can use the following code. The $1 and $2 in the replacement string refer to the parenthesized groups in the pattern. $1 is replaced by the text that matched the first group, $2 by the second, and so on, up to $9. The whole match can be referred to with $ampersand. It is possible to pass a function rather than a string as the second argument to replace. For each replacement, the function will be called with the matched groups as well as the whole match as arguments, and its return value will be inserted into the new string. Here's an example. This code takes a string, finds all occurrences of a number followed by an alphanumeric word, and returns a string that has one less of every such quantity. The \d plus group ends with the amount argument to the function, and the \pl plus group gets bound to a unit. The function converts amount to a number, which always works since it matched \d plus earlier, and makes some adjustments in case there's only 1 or 0 left. Greed. We can use replace to write a function that removes all comments from a piece of JavaScript code. Here's the first attempt. The part before the pipe operator matches 2 / characters followed by any number of new line characters. The part for new line comments is more involved. We use the caret, any character that is not in the empty set of characters, as a way to match any character. We cannot just use a period here because block comments can continue on a new line, and the period character does not match new line characters. But the output for the last line appears to have gone wrong. Why? The caret asterisk part of the expression, as I described in the section on backtracking, will first match as much as it can. If it causes the next part of the pattern to fail, the matcher moves back one character and tries again from there. In the example, the matcher first tries to match the whole rest of the string and then moves back from there. It will find an occurrence of asterisk slash after going back 4 characters and match that. If it is not what we wanted, the intention was to match a single comment, not go all the way to the end of the code to find the end of the last block comment. Because of this behavior, we say repetition operators plus asterisk, question mark, and curly brackets are greedy, meaning that they match as much as they can and backtrack from there. If you put a question mark after them, plus question mark, asterisk, question mark, curly braces, question mark, they become non-greedy and start by matching as little as possible, matching more only when the remaining pattern does not fit in the smaller match. And that is exactly what we want in this case. By having the star match the smallest stretch of characters that brings us an asterisk slash, we consume one block comment and nothing more. A lot of bugs in regular expression programs can be traced to unintentionally using a greedy operator where a non-greedy one would work better. When using a repetition operator, prefer the non-greedy variant. Dynamically creating regex objects. In some cases, you may not know the exact pattern you need to match against when you are writing your code. Say you want to test for the user's name in a piece of text. You can build up a string and use the regex operator on that. When creating the backslash s part of the string, we have the use of 2 backslashes because we are writing them in a normal string, not a slash encodes regular expression. The second argument of the regex constructor contains the options for the regular expression, in the case GI for global and case insensitive. But what if the name is DEA plus HL square brackets RD because our user is a nerdy teenager? That would result in a nonsensical regular expression that won't actually match the user's name. To work around this, we can add backslashes before any character that has a special meaning. The search method. While the index of method on strings cannot be called with a regular expression, there is another method, search, that does not expect a regular expression. Like index of, it returns the first index on which the expression was found, or -1 when it wasn't found. Unfortunately, there's no way to indicate that the match should start at a given offset, like we can match the second argument of index of, which would often be useful. The lastIndex property. The exec method similarly does not provide a convenient way to start searching from a given position in the string, but it does provide an inconvenient way. Regular expression objects have properties. One such property is source, which contains the string that expression was created from. Another property is lastIndex, which controls some limited circumstances where the next index will match. These circumstances are that the regular expression must have the global G or sticky Y option enabled, and the match must happen through the exec method. Again, a less confusing solution would have been to just allow an extra argument to be passed to exec, but confusion is an essential feature of JavaScript's regular expression interface. If the match was successful, the call to exec automatically updates the lastIndex property to point after the match. If no match was found, lastIndex is set back to 0, which is also the value it has a newly constructed regular expression object. The difference between the global and the sticky options is that when sticky is enabled, the match will succeed only if it starts directly at lastIndex, whereas with global, it will search ahead for a position where a match can start. When using a shared regular expression value for multiple exec calls, these automatic updates to the lastIndex property can cause problems. Your regular expression might be accidentally starting an index left over from a previous call. Another interesting effect of the global option is that it changes the way the match string on a string works. When called with global expression, instead of returning an array similar to that returned by exec, match will find all matches of the pattern in the string and return all containing the matched strings. So be cautious with global regular expressions, the cases where they're necessary, calls to replace, and places where you want to explicitly use lastIndex are typically the situations where you want to use them. A common thing to do to find all the matches of regular expressions in a string, we can do this using the matchAll method. This method returns an array of match arrays. The regular expressions given to match all must have G enabled. Parsing an INI file. To conclude the chapter, we'll look at a problem that calls for regular expressions. Imagine we're writing a program to automatically collect information about our enemies from the internet. We will not actually write that program here, just the part that reads the configuration file. Sorry. The configuration file looks like this. The exact rules in this format, which is a widely used file format, usually called an INI file, are as followed. Blank lines and lines starting with semicolons are ignored. Lines wrapped in square brackets start a new section. Lines containing an alphanumeric character followed by an equal character add a setting to the current section. Anything else is invalid. Our task is to convert a string like this into an object whose properties hold strings for settings written before the first section header and sub-objects for sections with those sub-objects holding the section settings. Since the format has to be processed line by line, splitting up the file into separate lines is a good start. We saw the split method in Chapter 4. Some operating systems, however, use not just a new line character to separate lines, but a carriage character followed by a new line. Given that the split method also uses a regular expression in its argument, we can use a regular expression like // r ? /n/ to split in a way that allows both \n and \r n between lines. The code goes over the file's lines and builds up an object. Properties at the top are stored directly into that object, whereas properties found in sections are stored in a separate section object. The section binding points at the object for the current section. There are two kinds of significant lines: section headers or property lines. When a line is a regular property, it is stored in the current section. When it is a section header, the new section object is created and section is set to point at it. Note the recurring use of caret and $sign to make sure the expression matches the whole line, not just part of it. Leaving these out results in codes that mostly works but behaves strangely for some input because it can be a difficult bug to track down. The pattern if match equals string.match makes use of the fact that the value of the assignment expression equals is the assigned value. You often aren't sure that your call to match will succeed, so you can access the resulting object only inside an if statement that tests for this. To not break the pleasant chain of else-if forms, we assign the result of the match to a binding to immediately use the assignment as a test for the if statement. If a line is not a section, header, or property, the function checks whether it is a comment or an empty line using the expression /caret \s asterisk parentheses semicolon pipe $sign parentheses / to match lines that either contain only white space or white space followed by a semicolon, making the rest of the line a comment. When a line doesn't match any of the expected forms, the function throws an exception. Code units and characters. Another design mistake that's been standardized in JavaScript regular expressions is that by default, operators like period or question mark work on code units, as discussed in Chapter 5, not actual characters. This means characters that are composed of two code units behave strangely. The problem is that the apple in the first line is treated as two code units and 3 is applied only to the second unit, whereas the dot matches a single code unit, not the two that make up the rose emoji. You must add the Unicode option to your regular expressions to make it treat such characters properly. Summary. Regular expressions are objects that represent patterns in strings. They use their own language to express these patterns. A regular expression has a method test to test whether a given string matches it. It also has a method exec that, when a match is found, returns an array containing all match groups. Such an array has an index property that indicates where the match started. Strings have a match method to match them against a regular expression and a search method to search for one, returning only the starting position of the match. The replace method can replace matches of a pattern with a replacement string or function. Regular expressions can also have options, which are written after the closing slash. The I option makes the match case sensitive. The G option takes the expression global, which among other things causes the replace method to replace all instances instead of just its first. The Y option makes the expression sticky, which means that it will not search ahead and skip part of the string when looking for a match. The U option turns on Unicode mode, which enables P syntax and fixes a number of problems around the handling of characters. It takes up 2 code units. Regular expressions are a sharp tool with an awkward handle. They simplify some tasks tremendously, but can quickly become unmanageable when applied to complex problems. Part of knowing how to use them is resisting the urge to try to shoehorn things into them that they cannot cleanly express. Exercises. It is almost unavoidable that in the course of working on these exercises, you will get confused and frustrated by some regular expressions' inexplicable behavior. Sometimes it helps to enter your expression into an online tool like debuggerx.com to see whether its visualization corresponds to what you intended and to experiment with the way it responds to various input strings. Regex golf. Code golf is a term used for a game of trying to express a particular program in as few characters as possible. Similarly, regex golf is a practice of writing as tiny a regular expression as possible to match a given pattern and only that pattern. For each of the following items, write a regular expression to test whether the given pattern occurs in a string. The regular expression should match only strings containing the pattern. When your expression works, see whether you can make it any smaller. 1. Car or cat. 2. Pop or prop. 3. Ferret, ferry, and Ferrari. 4. Any word ending in IOUS. 5. A whitespace character followed by a period, comma, colon, or semicolon. 6. A word longer than 6 characters. 7. A word without the letter E or uppercase E. Refer to the table in the chapter summary for help. Test each solution with a few test strings. Quoting style. Imagine you have written a story and used single quotation marks throughout to mark pieces of dialogue. Now you want to replace all the dialogue quotes with double quotes while keeping the single quotes using contractions like aren't. Think of a pattern that distinguishes these 2 kinds of quote usage and craft a call to the replace method that does the proper replacement. Numbers again. Write an expression that matches only JavaScript style numbers. It must support an optional minus or plus sign in front of the number, the decimal dot, and an exponent notation 5e minus 3 or 1e10, again with an optional sign in front of the exponent. Also note that it's not necessary for there to be digits in front of or after the dot, but the number cannot be a dot alone. That is, .5 and 5 dot are valid JavaScript numbers, but a lone dot isn't.